Good morning students. Welcome to 11th standard chemistry video class. We are discussing lesson 10 chemical bonding. In our last video class we completed up to bond parameters, namely bond length, bond order, bond angle and a bond enthalpy. In this video we have to start with the next topic, resonance. Resonance. What is resonance or resonance structure? When we write Lewis structure for a molecule, more than one valid Lewis structures are possible in certain cases. That the possible structures are said to be resonance or resonance structure. The concept of resonance is explained by considering the Lewis structure of carbonate ion with the formula CO3 2-. For writing the Lewis structure for carbonate ion, first we have to write the skeletal structure. In carbonate ion, it contains 1 carbon and 3 oxygens. The carbon is denoted by C and 3 oxygens are denoted as OA, OB and OC. Hence, the skeletal structure is shown here. Carbon is surrounded by 3 oxygens, namely OA, OB and OC. Next, we have to calculate the total number of valence electrons for carbonate ion with the formula CO3 2-. Therefore, total number of valence electrons is equal to 1 into 4 plus 3 into 6 plus 2. Here in 1 into 4, the 1 represents number of carbon and 4 represents number of valence electrons in carbon. In 3 into 6, the 3 represents number of oxygen and 6 represents number of valence electrons in oxygen, where 2 represents charge of carbonate ion, that is -2. Therefore, 1 into 4 plus 3 into 6 plus 2, which is equal to 4 plus 18 plus 2, which is equal to 24. Therefore, total number of valence electrons is equal to 24 electrons. Next, we have to place a single bond between carbon and oxygen A, carbon and oxygen B, carbon and oxygen C. Here it contains 3 bonds, that is 6 electrons. Totally we are having 24 valence electrons. Among the 24 valence electrons, 6 electrons are used in bonding. Remaining we are having 18 electrons. This 18 electrons to be taken as 9 lone pairs of electrons, and it is distributed in the high electronegative central atom, giving octet configuration. Now each oxygen atom is placed with 3 lone pairs of electrons. Hence, the distribution of these valence electrons given in the following structure. Now, carbon does not contain octet configuration, that is 8 electrons. Hence, complete the octet for carbon by moving a lone pair electron from one of the oxygen, that is oxygen A, and write the charge of the ion as 2- on the upper right side as shown here. Hence, this structure gives the Lewis structure of carbonate ion with the formula CO3 2-. In this case, we can draw 2 additional Lewis structures by moving the lone pair from the other 2 oxygens, that is oxygen B and oxygen C, thus creating 3 similar structures, which is shown here. Hence, in the structure 1, one lone pair electrons are moved from oxygen A to carbon. In the structure 2, one lone pair electrons are moved from oxygen B to carbon. In the structure 3, one lone pair electrons are moved from oxygen C to carbon. In these structures, the relative position of the atoms are same, but they differ in the position of bonding and lone pair of electrons. Such structures are called resonance structures or canonical structures, and this phenomenon is called resonance. It is evident from the experimental results that all carbon-oxygen bonds in carbonate ion are equivalent. An average of these three resonance forms gives the actual structure of the molecules. It is said to be resonance hybrid. It is important to note that carbonate ion does not change from one structure to another structure and vice versa. It is not possible to show the resonance hybrid by drawing a single Lewis structure. Hence, this structure gives the qualitative idea about the correct structure. Here, energy of structure 4 is lower than structure 1, structure 2 and structure 3. Hence, the difference in energy between structure 1 or structure 2 or structure 3 and structure 4 is called resonance energy. Here, structure 1, 2, 3 are more stable canonical structure, where structure 4 is resonance hybrid. Hence, we completed the topic resonance. Next topic, polarity of bonds. Here, we have to discuss two topics, namely partial ionic character in covalent bond and partial covalent character in ionic bond. First, we will discuss partial ionic character in covalent bond. A covalent bond may be formed between two same atoms or two different atoms. Consider a covalent bond is formed between two identical atoms or two same atoms. Here, the combining two atoms are same. Hence, they have same electronegativity value. Therefore, atoms have equal tendency to attract. The shared pair of electrons lies exactly in the middle of the nuclei of two atoms. For example, H2, O2, Cl2. In these examples, the combining two atoms are same. But in the case of covalent bond formed between two different atoms having different electronegativity value, the atom with higher electronegativity value having greater tendency to attract the shared pair of electrons towards itself. As a result, the cloud of shared pair gets distorted. It is explained with an example. Consider the example hydrogen fluoride, in which combining two atoms are hydrogen and fluorine. Here, hydrogen and fluorine has different electronegativity value. For hydrogen, the electronegativity value is 2.1. For fluorine, the electronegativity value is 4.0. The electronegativity value is based on Pauling scale. Here, fluorine is more electronegative than hydrogen. Here, fluorine attracts the shared pair of electrons towards itself. Hence, partial negative charge is formed on fluorine and partial positive charge is formed on hydrogen. Hence, the hydrogen fluoride bond is said to be polar covalent bond. Generally, in hydrogen fluoride, the bond formed between hydrogen and fluorine is covalent bond. Due to the different electronegativity value on the combining atoms, a partial positive charge and a partial negative charge is created. Hence the topic partial ionic character in covalent bond. Here, a very small, equal and opposite charges are separated by a small distance 91 picometer and is referred to as dipole. Next topic, dipole moment. The polarity of a covalent bond can be measured in terms of dipole moment, which is defined as mu equal to q into 2d, where mu is the dipole moment, q is the charge, 2d is the distance between the two charges. Here, dipole moment is a vector quantity since it has both magnitude and direction. The direction of the dipole moment vector points from negative charge to positive charge. It is shown here. The unit for dipole moment is coulomb meter. It is denoted by cm. It is usually expressed in d by unit. It is denoted by d, where 1 d by is equal to 3.336 into 10 to the power minus 30 coulomb meter. Consider diatomic molecules. Here, the molecule made of two atoms. The combining two atoms may be same or different. Here, we are having two types of diatomic molecules, nonpolar molecule and polar molecule. For a nonpolar molecules, they are having zero dipole moments, that is dipole moment equal to 0. Example, H2, O2, F2, etc. For polar molecule, they are having non-zero dipole moments, that is dipole moment is not equal to 0. Example, HF, HCl, CO, NO, etc. Molecules having polar bonds will not have dipole moment value. Consider carbon dioxide. It is a linear molecule. Even though carbon dioxide has two polar bonds, it has zero dipole moment. In carbon dioxide, the dipole moments of two polar bonds, that is two CO bonds, are having equal values, but they are in opposite direction. Hence, net dipole moment of carbon dioxide is given by mu is equal to mu1 plus mu2, where mu is the net dipole moment. Mu1 is dipole moment of first CO bond. Mu2 is dipole moment of second CO bond. Here the values are same, but they are in opposite direction. Hence it is represented here. In this case, mu is equal to mu1 vector plus mu2 vector. Substitute mu2 is equal to minus mu1. Therefore, mu is equal to mu1 minus mu1. Therefore, mu is equal to 0. For carbon dioxide, the dipole moment value is 0. In case of water, the net dipole moment is vector sum of mu1 and mu2. It is given by mu is equal to mu1 plus mu2. The dipole moment in water is found to be 1.85 d. The following are some dipole moment values for common molecules. The extent of ionic character in a covalent bond can be related to the electronegativity difference to the bonded atoms. Consider a molecule A bond B. Here A with partial negative charge and B with partial positive charge. Here Xa is electronegativity of A atom, Xb is electronegativity of B atom. Therefore, the electronegativity difference between atom A and atom B is given by Xa minus Xb. It is used to predict the percentage of ionic character. If the electronegativity difference Xa minus Xb is equal to 1.7, then the bond AB is 50% ionic character. If the electronegativity difference Xa minus Xb is greater than 1.7, then the bond AB has more than 50% ionic character. If the electronegativity difference Xa minus Xb is lesser than 1.7, then the bond AB has less than 50% ionic character. Hence, we completed partial ionic character in covalent bond. Next topic, partial covalent character in ionic bond. In our last topic, we discussed the partial ionic character in covalent compound. Here, we have to discuss partial covalent character in ionic compound. Consider lithium chloride, which is formed by ionic bond, and hence it has covalent character, and it is soluble in organic solvents such as ethanol. The topic partial covalent character in ionic compounds was explained on the basis of phenomenon called polarization. Here, in ionic compound, there should be an electrostatic attractive force between cation and anion. The cation with positive charge and anion with negative charge. The positively charged cation attracts the valence electrons of anion while repelling the nucleus. This causes a distortion in the electron cloud of the anion, and its electron density drifts towards the cation, which results in some sharing of valence electrons between these ions. Thus, a partial covalent character is developed between them. This phenomenon is called polarization. The ability of a cation to polarize an anion is called its polarizing ability, and the tendency of an anion to get polarized is called its polarizability. The extent of polarization in an ionic compound is given by the Fajans rule. The Fajans rule is explained on three factors, namely charge of cation and anion, size of cation and anion, and electronic configuration of cation. Let me discuss the Fajans rule. Fajans rule. First point. If the charge on cation and anion is greater, then they show greater covalent character. Higher the positive charge on the cation, greater will be the attraction on the electron cloud of the anion. Similarly, higher the negative charge on the anion, greater will be the polarizability. The conclusion is, increase in charge on cation or anion increases the covalent character. It is explained by taking some examples. Consider three ionic compounds, namely aluminum chloride, magnesium chloride, and sodium chloride. Here, aluminum with 3 plus charge, magnesium with 2 plus charge, sodium with 1 plus charge. Since the charge of the cation increases in the order Na plus less than Mg2 plus less than Al 3+. The covalent character also follows the same order. Sodium chloride less than magnesium chloride less than aluminum chloride. Second point, smaller size of cation and larger size of anion shows greater covalent character. Consider lithium chloride and sodium chloride. Lithium chloride is more covalent than sodium chloride. The size of lithium plus ion is smaller than sodium plus ion, and hence lithium plus ion has more polarizing power. Similarly, consider lithium iodide and lithium chloride. Lithium iodide is more covalent than lithium chloride. Since size of iodide ion is larger than chloride ion, hence I minus will be more polarized than Cl minus by the cation Li plus. Here lithium chloride and sodium chloride are explained by cationic size, where lithium chloride and lithium iodide are explained by anionic size. Finally, cations having Ns2, Np6, Nd10 configuration shows greater polarizing power than the cations with Ns2, Np6 configuration, or otherwise the cation with Ns2, Np6, Nd10 configuration shows greater covalent character than the cation with Ns2, Np6 configuration. It is explained by taking examples CuCl and NaCl. In Cu plus ion, the electronic configuration is stable electronic configuration of argon 3d10. In Na plus ion, the electronic configuration is stable electronic configuration of helium 2s2 2p6. In Cu plus ion, it has 3s2 3p6 3d10 configuration, where Na plus ion contains 2s2 2p6 configuration. Hence, we completed the topic partial covalent character in ionic bond. Let me stop up to this topic. The remaining topics that we will discuss in our next video class. Thank you.